Welcome to our presentation on mastering Stata. Today, we'll explore the critical but often overlooked aspects of data management, variable architecture, and the power of stored results. We will cover the journey from proper data property management all the way to automating post-estimation tasks, transforming your workflow from manual and error-prone to efficient and reproducible. Imagine trying to build a skyscraper on a weak foundation. That's what happens when you perform complex analysis on poorly managed data. We're here to learn how to build a strong foundation. To understand why this foundation is so crucial, let's first look at the consequences of not having one, the high cost of messy data. Think of your analysis as the tip of an iceberg. The visible part is the final table of coefficients and p-values for variables like GDP and education. But beneath the waterline lies the vast infrastructure: storage types, precision errors, variable labels, and missing value codes. A common scenario, as shown here, is a regression on GDP and education failing because a variable like GDP is stored as text, like 1,000, instead of a numeric 1,000. This single issue, a storage type problem in the infrastructure, invalidates the entire analysis and leads to zero observations. The consequences are severe. First, your results become non-reproducible. Second, you might draw invalid causal inferences. And third, countless hours are wasted on manual data cleaning that could have been avoided. This slide highlights that invisible data issues below the surface can sink an entire analysis, emphasizing the critical need for proper data management. A professional workflow in Stata follows a clear life cycle. It begins with ingestion, where you import raw data. The most critical phase is next, definition. This is where you immediately define variable properties like types and labels, setting the foundation for your entire project. After definition comes manipulation and analysis, where you transform variables and run your estimation commands. Finally, retrieval is the process of using Stata's stored results, R&E, to automate tasks and export findings accurately. This structured approach prevents errors and ensures reproducibility. For a survey dataset, you would first ingest the CSV file. Then, you would immediately define the gender variable by labeling 0 as male and 1 as female. Only then would you proceed to analyze the wage gap. Let's dive deeper into that crucial definition phase, starting with the most fundamental choice, the variable storage type. The first decision is the nature of your data. Is it text, categorical, or continuous? For text, use a string type like str# or strl. For categorical or integer data like IDs, Likert scales, or dummies, use an integer type. The byte type is the most memory efficient for dummy variables, as it only stores numbers from -127 to 100. For continuous or decimal data, use a real type, which includes float and double. While float is the default, it has precision limitations we'll discuss next. A key tip is to use the compress command after importing data. Stata will automatically choose the most memory-efficient storage type for each variable without losing information. Here we see the float versus double trap. A float variable can only store about 7 digits of precision. If you have a long ID number like 101011001, storing it as a float will result in a rounding error, changing its value to something like 1.00 e to the 9. The identity is lost. In contrast, a double variable stores up to 16 digits of precision, preserving the exact value of the long ID. This is why it's essential for identifiers. This has critical implications. First, Stata's special datetime variables must be stored as double to function correctly. Second, you should never merge datasets using an ID variable stored as a float, as the rounding errors will cause the merge to fail. Every variable in Stata has 5 key properties. The name is the case-sensitive identifier used in commands. The label is a human-readable description of what the variable is. The type is the storage method we just discussed, like byte or double. The format controls the display appearance, like the number of decimal places or date format, but does not change the underlying stored value. Finally, the value label maps numeric codes to meaningful text, for example, mapping the number 0 to the word male. The two golden rules are label everything to make your data understandable, and remember that changing the format is not the same as changing the type. For example, applying a date format per TD doesn't change a variable from long to double. After you run a command, Stata stores key results in memory. These are categorized into two classes. R-class results come from general commands like summarize, count, or tabulate. They contain things like the mean, standard deviation, or count. E-class results come from estimation commands like regress or logit. They contain more complex information, such as the coefficient vector, E of b, the variance-covariance matrix, E of v, and scalars like the r-squared, E of r2. A critical feature is that these results are temporary. They vanish as soon as you run the next command. Therefore, you must use them immediately. We use stored results for three main reasons: automation, like centering a variable using the stored mean, r of mean; export, like pulling the E of b vector into a publication quality table; and accuracy, as it eliminates copy-paste errors. After running summarize wage, you can immediately create a mean-centered wage variable by typing gen wage centered equals wage minus r of mean. This is faster and more accurate than manually typing the mean. So how do we access these powerful, albeit temporary, results? Let's look at the specific syntax. There are three primary methods for data manipulation. Generate replace is used for mathematical transformations, like creating a log transformed variable with gen log wage equals ln of wage. Recode is perfect for categorizing or binning continuous variables. For example, you can group ages into categories like young, using recode age 18 to 25 equals 1, young. Dstring encode are essential for fixing import errors. Dstring converts a numeric string like 123 into a numeric type, while encode converts a text string like male into a numeric type with an attached value label. A crucial best practice is to never modify the raw data directly. Always use generate to create a new variable for your transformations. This preserves the original data for auditing and verification. Additionally, use EViews to handle missing values systematically, ensuring they are correctly treated in all analyses. To manage variables, you can use several key commands. For inspection, describe gives a summary of variable properties, while codebook provides more detail. To add a description to a variable, use label variable. For instance, label variable price in USD. To create mappings for categorical data, you first define the label set with label define, such as label define sex lab 0 male, 1 female. Then you apply that label set to a variable using label values. For example, label values sex lab. Finally, to control display appearance, use the format command, which is especially useful for dates, like format datevar %td dd nn ccyy. An efficiency tip is to use the Graphical Variables Manager to make your changes. Then, Stata records the corresponding commands in the results window. You can copy and paste these commands into your do file to create a reproducible audit trail. With these basic commands, we can also implement more advanced logic for data cleaning and variable creation. When manipulating data, syntax is critical. Remember that the double equal sign, equals equals, is used for logical questions or checks, such as in an if condition. The single equal sign, equals, is used for assignment, which is the action of giving a variable a value. A common pitfall is forgetting to handle missing values in logical conditions. Stata system missing value, represented by a dot, is treated as positive infinity. So a condition like if income greater than 100,000 would be true for missing income. Always add a check like if not missing income to exclude them. The mvdecode command is a systematic way to convert specific numeric codes, like 999, into Stata's system missing value, ensuring they are handled correctly in all analyses. To create a dummy for high income, the command is gen high inc equals income greater than 100,000 if not missing income. Here, greater than is a logical check. Then you might use replace high inc equals 0 if income less than or equal to 100,000 to fill in the zeros, where equals is an assignment. After preparing our data, we run our analyses. Stata cleverly stores the results of these commands in a temporary memory space, which is our next topic. To see what's available in the raw class, you run a general command like summarize and then type return list. This will show you all the scalars and macros stored, such as rmean. Similarly, for the E class, you run an estimation command like regress and then type eReturnList. This displays the stored scalars, macros, matrices like EB, and functions. To use a stored result, you simply refer to it by its name. For example, display mean price and rmean will print the mean price. To see the coefficient factor after a regression, you can use matrix list EB. The best practice is to store these results immediately in a local macro or a scalar variable if you need to use them later in your script, since they will be overwritten by the next command. This slide focuses on the crucial first step of any data analysis, preparation and inspection. We begin by loading Stata's built-in auto dataset using sysuseauto clear. The describe command is essential here, providing a summary of each variable's properties, including its name, storage type, display format, and labels, as illustrated in the table below. We also use look_for_trunk to search for variables containing trunk. The practice points remind us to always know our data, check for unique identifiers using commands like isID, and scrutinize variables for any implausible or erroneous values before proceeding with analysis. Continuing our practice, here in Step 2, we focus on variable management. The code block demonstrates how to create a new variable, price K, by dividing the original price by 1,000 to represent thousands of USD. We then add a descriptive label and format it to 2 decimal places. Crucially, we use the recode command to transform rep78 into a binary variable, rep_binary. Values 1 and 2 are recoded to 0, labeled poor, and values 3 through 5 are recoded to 1, labeled good. The before and after graphic vividly illustrates this transformation. You can see how an original price of $49.99 becomes price K at 4.10, and rep78 value 2 is recoded to poor in rep_binary. The practice points highlight important concepts. Value labels provide human-readable meaning that sit on top of the code, so while you see poor, Stata actually processes the underlying number 0. Always remember to use the browse command to visually verify your recodes and other transformations, ensuring data integrity. Now for Step 3, Analysis. We run a simple OLS, Ordinary Least Squares Regression, regress price underscore K, MPG, rep_binary. This command estimates the effect of mileage and repair record on car price. Immediately after the regression, we run eReturnList. This command reveals all the results Stata has stored in the E class. We can see scalars like the number of observations, E of n, and the r², E of r2. More importantly, we see the matrices E of b and E of v. The matrix E of b is a 1×3 vector that contains the 3 estimated coefficients for MPG, rep_binary, and the constant. This is the key piece of information we will use for post-estimation. Additionally, E of sample identifies exactly which observations were used. This brings us to our final step, post-estimation. After running the regression, we can use the predict command to generate fitted values. The command predict y hat xb creates a new variable y hat containing the predicted price for each car. Crucially, predict automatically and internally uses the stored coefficient matrix, E of b. You do not need to manually type out the coefficients to calculate the predicted values. This process ensures mathematical consistency. The predictions are guaranteed to be based on the exact model you just estimated, eliminating any chance of typos or errors that would occur from manual calculation. We can then visualize the results, for example, by plotting the actual price and the predicted price against mileage to see how well our model fits the data. To summarize, achieving reproducible science in Stata relies on a three-part success checklist. First, define. Set your variable types and labels early in the process to build a solid foundation. Second, verify. Always check for precision issues, especially the float versus double trap